This video is about the mediating morphism maps that can be defined using universal and co-universals in a category. But the main purpose of this video is actually to prepare us to look at adjoint functors. So while mediating morphism maps are interesting in their own right, and we're going to spend most of this video looking at universals and mediating morphism maps based on universals, what makes them so important is that they can be used to define adjoint functors, which we'll see in a future video. So you'll see throughout this video, although we're focusing on results around universals, co-universals, mediating morphism maps, I'll do a couple little things that will help us to prepare in the long run for the main purpose of this video, which is sort of a stepping stone towards defining and looking at adjoint functors. So that being said, what are the mediating morphism maps? Well, mediating morphism maps are defined based on either a universal or a co-universal existing in a category. So we'll focus on the universal case for most of this video, but we will come back and revisit the co-universal case as we conclude near the end. So what is a universal again? Well, suppose we have some functor g going from a category D into a category C. Then a universal for CG, where C is just some fixed object in the category C, is a pair. So it consists of one object, U, which is an object in the category D here, and a morphism UC going from that fixed object C and C into the image of our object part of the universal here. So that's G of U over here. So we have the pair U, UC is universal for CG if for any object D and D, when F is a morphism going from C into the image of D under G here. So for any G of D here, and any morphism F going from C into G of D, there is a unique tau of F going from U into D such that this diagram commutes this triangle here. So that is the image of tau of F under G commutes with our universal morphism, the morphism part of our universal pair here, and our morphism F. So in other words, we can factor, we could say, any morphism F through our universal morphism here. So this would be G tau of F after UC. So suppose we have this universal U, UC for our functor G and our fixed object C. Well, in mathematics, we really like it when we can say for any one of these things, we can associate one of these things, right? Exactly one. Why do we like that? Well, because that's what we need to define a function, right? A function needs to take in any possible input here and have only one possible unique output for each one of those. So what can we say? Well, we can say that there's now a well-defined function going from the morphisms from C into any image GD into the morphisms going from U into D in the category D. So what we're saying is for any object D in the category D, there is a well-defined function, which we'll name in a second, which goes from, well, what are these morphisms? They're morphisms in the home set in the category C from C into G of D. And we're mapping these morphisms, such as F, into morphisms in the category D in the home set going from U into D. And it's defined by just mapping any morphism F from C into GD into the unique mediating morphism for F tau of f. And that function is well defined because we know that for any morphism f, any possible morphism f going to any possible GD, we have a mediating morphism tau of f, it exists, and it's unique, which is exactly what we need to define a function. So the next question is, what are we going to call this function? Well, it's the mediating morphism map, so let's call it M. And it's definitely going to depend on D, right? D is going to be a parameter to this function. But I'm going to do something a little strange here. I'm also going to index it by C, our fixed object C here in the category C. And so for this proof and for this entire video pretty much, this C actually won't matter because we're never changing this fixed C. We fixed it at the start when we defined our universal, and that's it. But we're going to see as we move towards adjoints that we actually want to vary over this C in this category as well. So we're not going to worry about it for now. For now, you can pretty much just think it's like, as a programmer would say, it's just hard-coded or something, right? It's not actually indexing anything. It's not varying. It's just to help us with the notation as we move towards adjoint functors. So the way it looks like it's doubly indexed over C and D, but it's actually just singly indexed, right? We're only varying over one thing here, which is D. And that's varying over all of the objects D in the category D here. So for the purposes of this video, it's just singly indexed over D until we get to the video on adjoints, where we actually will index over both. So for now, you can pretty much just pretend like the C is not there for this video. It's purely there as a notational trick. So this is the mediating morphism map here for D. And of course, for any universal U, C, we have a family of mediating morphism maps, one corresponding to each D in the category D. Well, there's two important things we can say right away about the mediating morphism map here. The first is that MCD is injective, because if the images of, say, F and F prime are equal, then tau of F is equal to tau of F prime, right? The mediating morphism maps for F and F prime are equal, which means that F equals G tau of F after UC, right, by this commutativity property here. But we can swap tau F in for tau F prime. So this is G tau F prime after UC. And that's the commutativity property for F prime, right? So that's just going to be equal to F prime. And so we have that F is equal to F prime. So anytime the images are equal, the inputs are equal. So MCD is injective for every D. But at the same time, MCD is also surjective. Why? Well, if we take any element of the codomain, say alpha going from U into D here, then if we take the morphism G of alpha after UC, so that's, imagine this is just alpha, not tau of F, it's this morphism here, which goes from C into GD. But then the universal property applies to this morphism here, right? So there's a unique mediating morphism blank here, G blank after UC, that equals G alpha after UC. Well, G, I wonder what morphism it is. Obviously it's alpha, right? It's already in this form. So obviously it's the unique mediating morphism that satisfies this equation here. So that means it is a unique mediating morphism, right? So there exists an element of the home set of CGD here that maps to it, right? We have MCD of this morphism, G alpha after UC, is alpha. So what does that mean? MCD is both injective and surjective. Thus, MCD is bijective. So we can actually, for any universal property, automatically define a bijection here, MCD. And we know that the inverse is given by this, right? So the inverse of MCD applied to, say, some H going from U into D is just going to be given by GH after UC, right? That's what we showed here when we showed it was surjective. Now, what happens if we apply this formula to a composite morphism? So set alpha to go from U to D again. And let's also add a morphism D going from D into D prime. Then this formula becomes MCD inverse, but if it's applied to D after alpha, then D goes into D prime. So this is actually going to have to be MCD prime inverse. And that's going to be equal to, by this formula, G D after alpha after UC. And then we can distribute this to get GD after G alpha after UC. And this is just this formula applied to alpha only, right? Instead of the composition. So we can recover our MCD inverse of just alpha here. So what is this formula saying? It's basically saying that if we apply this inverse of the mediating morphism map to a composition, we can actually just pull the first morphism out by applying the functor to it, right? So we kind of pull this D out of the inside of this function by just applying the functor D to it. Now, because this formula is true for any alpha going from U to D here, and because we have a bijection going from the morphisms from U to D to the morphisms from C to GD, we know that we can replace any instance of alpha in this formula here with its representation as MCD of some F, like this, going from C to GD, right? Every alpha gets mapped to by the mediating morphism map. So what we'll say is that this actually implies that we can replace alpha by, so this would be MCD prime inverse of D after, and so this would be MCD of F, and that's going to be equal to, on this side, GD after, well, it's just going to be MCD inverse of MCD of F, so that's going to cancel, and we're just going to get F, and that's because MCD is bijective, and this, because of that fact also, is going to be true for any F going from C to GD, right? By making this true of every alpha from U to D, and by having a bijection going into these morphisms from C to GD here, we can say that this is going to be true for all of these F's, right? Well, then we can apply MCD prime to both sides. So if we put this side first, we get MCD prime of GD after F is equal to, and then this is obviously going to cancel with MCD prime, so we just get D after MCD of F. Now this here, GD after F, is the same as follow by GD applied to F, right? Remember our function follow by, so this would be MCD prime after follow by GD applied to F, right? This followed by GD just does exactly what you would think. It follows F by GD, which is what we have here. And same thing on this side, right? This is follow by D applied to MCD of F. So this is follow by D after MCD of F. And this is for all F going from C to GD. And so what does that mean? That means we have MCD prime after follow by GD is equal to follow by D after MCD. In general, right? For any F. This is the equation for any F, and this is the general morphism or function equation. And moreover, this general version is true for all D in D, right? For every morphism D in the category D. Now, if we take all of these equations together for all D, what does this tell us? Well, it tells us something really important, actually, right? What was the context where we previously talked about follow by morphisms and precede by morphisms? It was in the context of home functors, right? Covariant and contravariant home functors. So for example, follow by D is what? It's the image of D under the covariant home functor, home U blank, for example. And what is followed by GD? Well, it's the image of D under the composition of G with the covariant home functor, right? So we can write it compactly as home C G blank, and this is equal to G followed by the covariant home functor home C blank. And in that context, this kind of an equation should look really familiar, right? It looks like a commutativity property or a commutativity square. So, for example, if we take D going from D to D prime, and then we map it by up here, home CG blank, and down here by home U blank. Then here we're going to have our follow by GD morphism. And here we're going to have our follow by D morphism, right? These are the images of D under the two covariant home functors. And this equation tells us that for every component, we can fill in the commutativity square with MC and then D for that component, right? So this would be MCD prime, right? So this is actually proof that there's a natural transformation going from this composite home functor into this home functor, right? And not only that, but we know that it's given by the mediating morphism maps, MCD, for all D in the category D. But since we know that each one of these components is actually a bijection, and that these are bijections in the category of sets, otherwise known as isomorphisms, what we actually have here is a natural isomorphism. Right? So to sum up, because this equation is true for every D, that means that this commutativity square, which is this equation here, is true for every component D. And so there's a natural transformation going from this composite home functor, home C G blank, to the home functor home U blank. And not only that, because every component we know is a bijection, this forms a natural isomorphism. So that's pretty cool, right? Just based on the definition of a universal, we were able to get all of this for free. We were able to define the mediating morphism maps, show that they're well-defined functions, show that they're bijective, give their inverses, and not only that, but we can show that the collection of mediating morphism maps for every object in D actually forms the set of morphisms that represent a natural isomorphism between two covariant home functors in the category D, or defined on the category D, right? And obviously a natural isomorphism is not an easy condition to satisfy, so that's pretty powerful that we're able to get it just purely based off this definition. So to be a bit more specific, what have we actually proved so far? Well, let's take these three statements in red, so maybe call this 1, call this statement 2, and call this statement 3 down here. We've proved that 1 implies 2, right? If we have a universal UUC for the pair CG with these mediating morphism maps, then MCD is bijective, and this is its inverse, right? And then when we proved 3, we actually started with 2 as our starting point, right? We applied this formula here to this composite morphism, and that's how we started the proof. So what we've actually proved is that 1 implies 2, and 2 implies 3. Now, it's not hard to show that 3 actually implies 2 as well. We just have to add one quick assumption, which is we need to fix what UC actually is. So in the case where we have this universal here, right, one example of an F we could take would just be UC itself, right? And if that's the case, then what would we need to have over here? Well, it would be a morphism going from C into GU, so it would be a morphism going from U to U. And it would need to uniquely make this triangle, which isn't really a triangle, it's just sort of one morphism, commute with something that follows it, right? Well, it would just be 1U, right? This would have to be 1U over here, and then because functors map identities to identities, we would end up with G tau of F, or G tau of UC, I should say, would be also 1 GU, right? So what we need to say is that in this case, what we want is to set UC to be equal to the inverse of MCU of 1U. Right? Because that's what we need to have up here. So let's just add this as an assumption to 3. So if we start with the fact that there's an MCD, which is a natural isomorphism between these two home functors, and we define UC to be the inverse of 1U for MCU, then this logic actually just runs in reverse. So we start with this general expression for all D, right? That's the definition of a natural transformation. And then if that's the case, then we can just apply it for any F from C to GD, right? So that's what we've done here. And then if that's the case, we can expand out followed by GD into GD after F, right? That's how that's defined. So that works. And if that's the case, then we can apply MCD prime inverse to both sides, right? And so we get back to here. And now we can even take this step again, right? MCD is bijective. So if that's the case, then we can replace F with MCD inverse of alpha, and we will get that expression, which is true for all alpha, right? The same way we did it this way. Because it's a bijection, we can replace F with its representation as MCD inverse of alpha, where alpha goes from U to D. So if that's the case, then we get MCD prime inverse of D after. So this would be MCD of MCD inverse of alpha. So this would just be alpha. And here we would get, here we would get GD after MCD inverse of alpha, right? So we recovered this expression for all alpha from U to D. And for all D, going from D to D prime. And then what we can do is we can just apply this formula here that we just got from this step here, and we can use it to get back the expression we need here. And so to do that, we would have to replace D with H, and we would have to replace alpha with 1U, right? And that makes sense because if D goes from D to D prime, then in our case, when we replace it, it would go from U to D. So D is U in this case, and D prime is D in this case. A little bit confusing, but we're just substituting in, right? And then 1U, well, D is U, so that makes sense, right? So this morphism goes from U to U, and so 1U would make sense. So we can apply that to get MCD. So this is D prime, so we said D prime is D, so just MCD inverse of H, right? So this would be H after 1U, so it would just be H equals GH now, right? Substituting in after, well, this is MCD where D is U, so this is MCU inverse of 1U. But MCU inverse of 1U, that was our assumption. We set that to be UC. So we have GH after UC, right? And that's the exact expression we need. MCD inverse of H is equal to GH after UC. So that means that 3 also implies 2, right? If we start with the assumption of this natural isomorphism here between the composite home functor home CG blank and the covariant home functor home U blank, then we can pretty much run our logic step by step in reverse, and we'll get back this expression that we needed. And again, this is for all D and D, and for all H going from U into D for all those D. And of course, it'll be bijective for each one because this is a natural isomorphism, right? So if there's a natural isomorphism in the category of sets, that means every component, every MCD has to be a bijection. So we've seen that 3 implies 2. So let's just sort of clean this up and summarize where we are, and then we can complete the proof. So here's the full statement of the theorem that we're almost finished proving, where there's just one more step. So suppose G is a functor going from D to C, and that C is some fixed object in C, and U is some fixed object in D. Then let the function MCD from home CGD in the category C to home UD in the category D. So that's the morphisms from C to GD going into the morphisms from U to D. For all D and D, be a family of bijections. So not only are they functions, but they're bijections for each MCD, where MCD only varies over the D, not over the C. So set UC equal to MCU inverse 1U, as we assumed before, then the following are equivalent. So UUC, the pair, is universal for CG, and our MCD family are actually the mediating morphisms for that universal, given by MCD of F here is the unique tau of F that satisfies F equals G tau of F after UC. Right, that's the property we looked at before. And the second statement that's equivalent to the first and the third is that MCD all satisfy MCD inverse of H is given by GH after UC for all D objects in D and for all H from U to those objects D. And finally, the third is that MCD is actually a natural isomorphism going from the composite home functor home CG blank into the covariant home functor home U blank. So why are we not quite finished the proof yet? Well, we've proved that 1 implies 2, and we've proved that 2 and 3 imply each other. So in order to have equivalency, we need to prove something implies number 1, right? So let's actually prove this one here, going from 2 into 1. So let's prove that if MCD all satisfy this equation, then UUC is universal for CG. So here we're proving the last step from 2 to 1. So suppose MCD inverse of H is equal to G of H after UC for all D and for all H. Well, then we need to show that it has this universal property here, right? UC is universal for CG. So take the F from C to GD, and we need to find the unique mediating morphism, right? So if that's the case, then notice that MCD of F goes from U into D, right? So we can apply our formula to it here because this has to be H from U to D. So on this side, MCD inverse of MCD of F, so they cancel and we just have F. And that's equal to, on this side, G MCD of F after UC, which is the commutativity property that we need here, right? We have F is equal to G of the image of F under our supposed mediating morphism. We don't know it's a mediating morphism yet, but M. So we have the commutativity property is satisfied, and we just need to make sure it's the only one where the image satisfies that, right? So, and if f equals GD after UC, well, then we can apply our formula again to this side, right? To get this is MCD inverse of D here, and that's equal to F, but F is equal to MCD inverse of MCD of F. Right? Because they just cancel out and we get F back. So if that's the case, then since MCD here and MCD inverse are bijections, we must have that D. So because the outsides are equal, the insides must be equal, right? Because the outputs are equal, the inputs must be equal because it's a bijection. So D equals MCD after F. And so that means that it's unique, right? It's the only one whose image satisfies this property here, which is exactly what we needed to show for the universal property. And MCD are, in fact, the mediating morphism maps, just as we had hoped. So this is no longer a question, this is proved, so we can just remove these arrows. Everything is equivalent to everything, and that's QED. So overall, it's a pretty powerful result, right? And it gets at some of the fundamental concepts that we've talked about in all our previous videos, such as universality conditions and natural isomorphisms. And so now we know that any universal is enough to guarantee the existence of a natural isomorphism and vice versa. And not only that, but all we need to get either of them is just a set of bijections that satisfy this property where this is what UC is, right? So if we can ever find a family of bijections that satisfy this equation, then we have guaranteed the existence of both a universal and a natural isomorphism between home functors. So as mentioned, we'll conclude by talking about the co-universal case. So as a reminder, here's the co-universal diagram here. So if there's a functor f going from C to D, then dVd, the pair dVd, is co-universal for D and F. If for any f like this going from FC into D, and again, that's for any C in C, any FC, then there must be a unique mu of f going from C to W in C this time, such that the image of mu of f under f, the functor f, makes this diagram commute, right? This sort of opposite triangle commutativity property. Well then, we're in a very similar situation to the universal case, right? We have for every morphism f here, there is a unique mu of f, so we can define a well-defined function, LCD, which we might call the mediating morphism map for the co-universal, or maybe even the co-mediating morphism map, if you will. And that goes from these morphisms here, going from FC into D, into the morphisms going from C to W in C. And again, that's for all C and C. And as with MCD, LCD is bijective. The inverse is given by VD after F of H for any H going from C to W. And that's where VD is defined as LW, the inverse of 1W, the identity on W. So you can see this is where the double index CD here comes into play, right? Because now we're still only varying over 1, but now we're varying over the other index, all the C's in C, right? And D just stays fixed. D just stays the same here. So we can see kind of why that was helpful to add that. And then we'll see it even more when we start to combine the universal and co-universal case when we start talking about adjoints. So If you want, you can prove these three statements just to check, but once we have that in place, we can basically state the dual of the theorem that we just proved for the universal case. So if there's a functor f going from C to D, D is some fixed object in D, and W is some fixed object in C, then let LCD going from the home set from FC into D, and the going into the home set from C to W for every C in C be a family of bijections, and we set VD to be equal to what we set up here. Then the following are equivalent. So W VD is co-universal for DF, and LCD are the mediating morphisms. LCD of F equals the unique mu of F, such that this triangle here commutes. That's equivalent to LCD all satisfy LCD inverse of H equals VD after F of H for all C and all H going from those C into W. And finally, that there's a natural isomorphism going from, in this case, home F blank D to home blank W. And note that these are now contravariant home functors, not covariant home functors, right? The blank is in the start. And once again, this is a composite where we apply F first and then the contravariant home functor. So thanks to the fact that this is a dual, we basically get this for free. So we could call it QED, but we didn't really prove anything. So this is the statement for the co-universal case. And so in a future video, we'll see how we can actually combine the universal and the co-universal case. And when we do that, that's when we get an adjoint.